Have you ever stopped to wonder how the completely invisible building blocks of our world actually connect to create, well, everything? Everything we see, touch, and breathe? The answer lies in this incredibly fascinating story about atomic friendships. Chemists call it Valence Bond Theory. And it's really a story of how atoms reach out, overlap, and quite literally build the universe together.
So, here is our roadmap for today. We're going to treat this like chapters in a grand story. Chapter 1, the quest for stability. Chapter 2, orbitals, where electrons live. Chapter 3, the atomic handshake. Chapter 4, sigma versus pi bonds. And finally, Chapter 5, nature's remodeling project.
Okay, let's dive into Chapter 1, the quest for stability.
Imagine a world where atoms are like people, each searching for stability, for completeness, for a sense of being whole. I love that quote because it perfectly captures the fundamental principle of chemistry. You see, atoms aren't just these cold, static, lifeless spheres. They're actually constantly driven by a single overriding desire, which is to achieve a lower energy state. Because in the universe of physics and chemistry, lower energy directly equals greater stability.
Now, some atoms, like the noble gases helium and neon, they're basically already living the dream. They're in a state of perfect low energy with completely full outer shells. But take a look at the gaps for the rest of the elements here. Hydrogen has 1 electron, but it really wants 2. Oxygen has 6, but it needs 8 to hit that low energy sweet spot. Carbon has 4, needs 8. Nitrogen has 5, and it also needs 8. They all have these critical gaps in their valence shells, and so they have to take action.
Think of it like a neighborhood. Atoms absolutely thrive by sharing resources. They share tools, they share space, and crucially, they share electrons. When two adjacent atomic neighbors share electrons, they both achieve that coveted low energy state. That mutual use of an electron, that physical sharing of space, that's exactly what we call a chemical bond.
Which brings us nicely to Section 2, orbitals, where electrons live.
Now, what's really interesting here is how this brilliantly dispels the old myth of electrons just floating around in random, chaotic circles around a nucleus. They actually live in very specific, highly defined three-dimensional regions of space, which we call orbitals.
And the physical shape of the orbital completely dictates how an atom can connect. For instance, the s orbital is perfectly spherical, holding a maximum of 2 electrons. But then you have the p orbitals, which are shaped much more like dumbbells. There are 3 of them, and they point along the x, y, and z axes, sitting completely mutually perpendicular to one another. Grasping these specific 3D rooms where electrons live, that is the absolute, vital key to understanding why bonds form and what they physically look like when they do.
Let's move on to Section 3, the atomic handshake.
The real magic here happens through something known as orbital overlap. When 2 atoms approach each other, their orbitals actually merge. They end up sharing the exact same physical region of space. And as this overlap happens, the electrons in that shared space are simultaneously attracted by the positively charged nuclei of both atoms. This incredible dual attraction drops the overall energy of the system dramatically. Stability rises, and boom, a bond is born.
To really visualize this, just think of a handshake. A bond only forms because 2 hands, or 2 orbitals, physically occupy the exact same space. If there's 0 overlap, there's 0 bond. And exactly like human interaction, a greater overlap means a firmer, much stronger handshake. This single, elegant idea is literally the entire foundation of valence bond theory.
All right, Section 4, sigma versus pi bonds.
Depending on exactly how atoms approach one another, they form entirely different types of bonds. When orbitals approach directly, right, head to head, they form what's called a sigma bond. This is a very strong, very direct overlap. And because it's essentially a straight line between the atoms, the molecule can actually rotate completely freely around that axis. But sometimes, orbitals approach laterally, side by side. That forms a pi bond. Pi bonds are definitely weaker because that sideways overlap just isn't as deep. But crucially, because they lock the atoms together parallel to one another, a pi bond prevents free rotation. It completely locks the molecule into a rigid shape. These 2 very different types of overlaps are the secret sauce behind double and triple bonds. A standard single bond, that is always 1 strong sigma bond. But if atoms need to share more electrons, they'll form a double bond, which is 1 sigma bond plus 1 pi bond. And a triple bond goes even further. You get 1 sigma bond flanked by 2 pi bonds. Triple bonds are the strongest of the bunch because, quite simply, more bonds mean more overlap, and more overlap means maximum stability.
And this brilliantly illustrates exactly how those overlapping clouds look in physical space. You can clearly see the green sigma bond created by that direct, head-on overlap,
And then right next to it, contrast that with the more delicate yellow pi bond occurring laterally above and below the bonding axis. It's just a beautiful visual representation of how these invisible forces structure themselves.
Let's move into our final chapter, Section 5, Nature's Remodeling Project. Sometimes an atom's existing orbitals just aren't quite good enough to form the specific bonds it needs. Take carbon, for example, the master builder of all organic life. In its normal state, it has mismatched s&p orbitals, which is super inefficient for complex building. So think of a hotel manager knocking down mismatched, awkward rooms to rebuild perfect, identical ones. Nature does exactly this. Carbon mixes its distinct s&p orbitals together to create completely new, perfectly identical hybrid orbitals. We call this incredible process hybridization, and it entirely dictates the 3D geometry of the resulting molecule. If carbon mixes one s and 3 p orbitals, it creates 4 sp3 hybrids that spread out into a tetrahedral shape with angles of exactly 109.5 degrees. If it only mixes one s and 2 p orbitals, it makes 3 sp2 hybrids, which lie totally flat in a trigonal planar shape at 120 degrees. And mixing just one s and one p creates 2 sp hybrids pointing in exactly opposite directions, making a flat 180-degree line. Carbon is literally remodeling its own electron rooms so it can point them directly at bonding partners for maximum, incredibly stable overlap.
And you can see the visual proof of this atomic renovation right here. The mathematical reality of these newly built orbitals perfectly predicts the real-world 3D geometry of the molecules. You've got the 3D tetrahedral structure of methane, the flat trigonal planar layout of ethene, and that perfectly straight line of acetylene.
So, the crucial point we need to take away here is that this isn't just some abstract whiteboard chemistry. This is the literal reason our world looks and feels the way it does. Hybridization is why the molecular world has shape. Without it, every bond would be weak, misdirected, and totally chaotic. But because atoms can remodel their orbitals to maximize their handshakes, carbon can build the rigid tetrahedra of diamonds, the flat planes of alkenes, and the incredibly complex twisting architecture of human DNA.
Ultimately, it all comes back to a single elegant truth. Atoms are just trying to achieve a stable outer shell. But if mastering these relatively simple atomic handshapes, these orbital overlaps, allows nature to build everything from rigid diamonds to human DNA, well, it begs a pretty massive question. As scientists learn to artificially manipulate these very hybridizations in the lab, what completely impossible world-changing